All right, well, it is time to talk about electron structure. This really sets the stage for whatever you want to do with chemical reactivity, chemical changes, and even a lot of physical properties are controlled by electron structures. So let's get into it. Before we can study reactivity, we've got to really understand the nature of the electron cloud. And so our kind of steps, things we've got to be able to do as prerequisites for studying chemical reactions is we first need to understand what's called the ground state structure of the electron. And basically what ground state means is it's for an atom that's neutral. So same number of protons as electrons, and it's in what we'd call a low energy condition. It is possible for um, atoms to be energized essentially, and that can cause the electrons to jump around a little bit from where they would normally be in the electron cloud. If you um, pretty much see anything that produces light, chances are you are um, seeing electrons jumping around. Really, color and light and all of that are the result of the electrons. So we kind of at this level of chemistry, we deal with everything in terms of the starting point for electron structures, and we can talk about how electrons move from there. We need to identify the electron configuration for an atom, and that comes with learning each electron's address, and that's in quotes because that's not what it's formally called, but essentially each electron in the electron cloud has a specific designation. That designation is based on a four-part address. Would be analogy. The analogy would be, wherever you live, you probably have a number, whether it's an apartment number or house number, um, the street name, the city, the state. So you have a multi-part address, and the electron has one as well that's made up of four different parts. We'll also look at the limitations of some of the rules that you may have picked up earlier in your study of chemistry or the sciences. One of them is the 2n squared rule. The 2n squared rule basically says that for any particular energy level of the electron cloud, if you plug in the number of the energy level, that tells you how many electrons in total can fit on that. So if we plug in 1 squared is 1 times 2. So the first energy level can hold 2 electrons. If we plug in 2, 2 squared is 4 times 2 is 8, and so on. It's a kind of a fun trivia of a rule, but it isn't of that much use to us, and I'll show you why later on. And also limitations of what's known as the octet rule. The octet rule is that magic 8 rule that you heard about in biology that does have importance in understanding electron configurations, but it also has limitations in that it's not every element is seeking to fill the octet all the time. There's other things that can happen that really steer electrons or the steer atoms toward chemical reactivity other than just the number 8. Then we need to identify the potential valence electrons. Valence electrons are the outermost electrons of the electron cloud, and they are the ones that really participate in chemical reactions. So, we kind of go through and identify the entire electron structure of the atom, but in reality, we're only concerned about specific electrons that are available to participate in chemical reactions, and those are what we call the valence electrons. And then we also can have an understanding of exactly how much energy it takes to bring those electrons from the ground state to some sort of an excited state, or to completely knock the electron off of the atom and ionize it, so to give it a charge. And we looked at how, sodium pretty easily loses 1 electron to become a sodium ion that has a positive 1 charge. So you could take that sodium atom and have an electron that just gets excited, so it just moves out a little bit, but doesn't actually leave the atom. Or you can have a sodium atom where the electron's actually removed, or it's sent somewhere else, or it's somehow released completely from the atom, and then that would be ionized. So it takes different amounts of energies to excite electrons versus ionizing them. And all of that knowledge, if you know all of this, then that gives you a major, major insight into the chemical reactivity of the elements. So the electron cloud, lots of models that have been thrown around over the years. We looked at Bohr's model, which basically had the electrons in these orbits around the nucleus. And so, this little diagram showing how, this particular electron here could be excited out to, a different energy level than what it's in, and then it tends to fall back. And when, if electrons take in energy to go outward, they release the energy coming back. So if you have, let's say, a glass tube filled with gas and you inject an electric current into that gas tube or glass tube filled with gas, then the electrical energy will cause the electrons to head out. And then when they fall back, they emit that energy in the form of light. And that's a lot of what goes on in a very simplified form in fluorescent light bulbs. But Schrödinger comes along and takes Bohr's model, which sounds so easy, and says, that's not really the way they go. So another analogy is a set of stairs. So there's a picture over here of a set of stairs, and you know that if you walk up a set of stairs, it takes some energy, and so the energy of the stairs would be higher going up than going down. So the energy increases as you go up the stairs. A lot of this is related to the good old myth of Sir Isaac Newton down here. No, the apple did not fall and hit him on the head. He may have observed an apple falling and had a eureka moment. But in physics class, when I teach it, I talk a lot about how the amount of energy something has is really a measure of how much it's going to hurt when it hits you. So if we take a little cartoon of Sir Isaac Newton here, and let's say the apple fell from here and it hit him in the head, it would be a little doink. But if the apple fell from much higher and had greater time to accelerate and hit him in the head, it would be a bigger doink. So the idea is that closer to the nucleus is a lower energy than further out from the nucleus. So an electron that wants to be at a low energy is going to come in and fill low on our set of steps. And then the next one presumably is going to want to fill up here, is going to want to fill up here, is going to want to fill up here. So a little bit like Plinko, the electrons are going to come into the atom and they're going to find their way down until they reach the lowest energy state that they can fit into. And that again gives us an idea of why we call it the ground state. So in order to understand the electron cloud, we have to figure out what these stairs actually look like, because Bohr made it very simple and said, well, they would look just like this. So you would just fill up electrons on the steps and they would be in very specific levels. You can't have an electron that's halfway in between steps. It has to be on a step. And so this is the term in one of the other videos we looked at, is that the electron cloud is quantized, meaning that it's broken into specific segments, hence the term then quantum mechanics, looking at how this process occurs. And we do know that it is quantized, but the levels aren't necessarily all nice and neat and even like a stairway is. It's more like, if you've ever been in a very old building that has been added onto a lot, you may have noticed it going from one section of the building to another that the floors don't actually line up. You may have to go from up a couple of steps, or there may be a ramp or things like that. So one side of the stairs may be a little higher than the other side of the stairs, and we have this one's a little bit lower, and they're just not always all lined up. BTA actually isn't bad. We have the 100 level classrooms and the 200 level classrooms and the 300 level classrooms. And if you're on the 300 level, you're on the main level of the building, then all of the classrooms are at the same level. But as if you put an addition on the building, then depending on how it's built, it may not all line up. And I know of another high school I've been in that it's only a 3-story building, but they have 100 level, 200 level, 300 level, 400 level, 500 level, 600 level, 800 level, and 900 level rooms. No 700. I don't know why, but the building has been added on so many times, and the floors are so inconsistent as you walk from one end of the building to the other that they actually give different sections different numbering, even though the building really is only 3 floors tall, kind of like ours. So there's all these analogies of the electron cloud being like a set of stairs, or being like an apartment building with each floor of the apartment building. But Schrödinger would say, yeah, it's a little more complicated than that, except of this idea of electrons filling from low energy to high energy. Whatever shape the floors are in the apartment building, whatever shape the steps are, the electrons are going to occupy those steps from lowest to highest. And I guess I should use the term occupy because the steps don't really exist. The steps are a representation of where the electrons are, but it really is the electrons that form these energy levels. The energy levels do not exist without the electrons there to create that space, or to occupy the space that they are predicted to occupy by Schrödinger's equations. So it's kind of important. It's tough to visualize what the electron cloud looks like without some sort of analogy, but you have to remember that the electrons make the cloud. So when we talk about an electron filling an orbital, we're really saying that that electron is creating that orbital. So this is more of what Schrödinger's equation predicts. So if you take those 4 parts, of the electron's address, and you make a function out of those, f of n, l, m, and what is it, p, spin state. You take those 4 parts of the electron's address, the 4 variables, and you plug it into Schrödinger's equation, you get 3-dimensional graphs that look like these little drawings here. So the simplest of the shapes is the sphere shape, which is called an S sublevel. The more complicated shapes that you see in the next row are called p orbitals, or the orbitals of the p sublevel. The even more complicated ones here all go along with the letter D. So that's called a D orbital, or a D sublevel. And then the really fancy ones down here, and you remember these are 3-dimensional plots of the output of a 4-variable equation. So, it's pretty high in math, but we're actually able to visualize some of these now using scanning tunneling electron microprobes, where we can actually take and trace the top surface of an atom like this and see kind of the outline of these fancy electron cloud shapes. So we're beginning to take Schrödinger's predictions and turn them into observations. So the F ones are even more complicated. So you can see that there's one possible shape to an S sublevel. So there's one possible there. There are 3 possible shapes to a P sublevel. There are 5 possible shapes to a D sublevel, and there are 7 possible shapes to the F sublevel. So SPUDFA 1, 3, 5, 7. important thing to know going forward, that the number of potential orbitals associated with each letter designation for the sublevel. So S, P, D, F, 1, 3, 5, 7. Got to know that. Okay, where are we at? All right, so this is actually more what the electron cloud looks like in terms of energy levels. So again, we have our increasing energy over here on the side, and you can see here we have those energy levels that Bohr talked about. So levels 1, 2, 3, 4, 5, 6, and 7. And we would give those the symbol N. So N is the principal quantum number. And this is sometimes referred to as a shell, but principal quantum number with the symbol lowercase n is kind of the proper designation for it. So there are 7 possible principal quantum numbers: 1, 2, 3, 4, 5, 6, 7. And then for each principal quantum number, there's certain sublevels that can exist. And a lot of that has to do with space. Remember that this is the nucleus is way down here at the bottom of the diagram. So it's way down here. Hopefully that fits on the screen. And then all of these electrons are progressively further away from the nucleus as you go with increasing energy. So down close to the closer to the nucleus, even though we're still, the marble in football stadium analogy, there's less space. So the one principal quantum number, so principal quantum number 1, only has room for an S sublevel. The second principal quantum level has enough room for an S and a P. And the third principal quantum level has room for an S, a P, and a D. And the fourth has S, P, D, and F. And we'll kind of look at how this all fits together later on. But you basically, an S always comes before a P always becomes for a D, and an F always comes after the D. So S, P, D, F. So you see we go 1S, whoops, lost my pen. 1S comes first. Then as we're moving up, 2S, 2P, 3S, 3P. But notice what happens right here. This is where Bohr's model falls apart. The 4S sublevel, so principal quantum number 4 in its S sublevel, is at a lower energy than the 3D sublevel. So the third quantum number, the third quantum level, is not full, but because this 4S shape is easier to make, the electrons will actually begin building that fourth S sublevel before they have enough energy to start constructing the 3D sublevel. And so this is where the octet rule, you have to be careful how you word it. It's not that an energy level is full. It's that an energy level has a specific combination of electrons that adds up to 8. And where we see that happen on here is every time we fill an S and P sublevel. So one piece we'll get is that each one of these lines can hold 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And so every time that happens, here, 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 and here, those are your ideal gases. So, helium, neon, argon, krypton, all of those on up. Those are representing an S, what we really call an sp octet, which is when the outermost electrons of an atom are the ones that fill that S and P set of 8 electrons, 2 in the S and 6 in the P. So quite a bit there. And this diagram is one we really need to become familiar with. Eventually, I'll teach you how to create this whole thing from memory. It's not that bad because it's a repeating pattern. And we all know that chemistry is all about repeating patterns because we have a big table called the periodic table. And the word periodic literally means in a repeating pattern. So essentially, the reason we call it a periodic table is because it's ordered based on the electrons that form a repeating pattern of shapes. So to identify a specific electron, one of the principles that we have, one of the kind of rules for it is the Pauli exclusion principle, which basically says that no two electrons can have exactly the same address. So no two electrons can have exactly the same principal quantum number, sublevel, orbital, or spin state. So the principal quantum numbers are symbol n, and that is the sequence 1 through 7. The sublevels, or the subshells, are represented by the letters S, P, D, and F. The orbitals are specific orientations of those sublevel shapes. So like the S was the sphere, the P was kind of those double lobes, and the D's and the F's had progressively more complicated shapes. And if I think I can flip back here, you see these little orientation designations down here, whoops, that are along with each one, indicating each of the possible orbitals, orbital orientations that go along with the different sublevels. And then spin state is the final piece of the address. And basically you have two choices there, an upspin or a downspin. So there are 7 possible principal quantum numbers. There are 4 possible sublevels. There are 1, 3, 5, or 7 possible orientations, depending on whether you're in an S, a P, a D, or an F sublevel. And then there are 2 possible spin states. So what that means is that any one of these orbitals can hold at most 2 electrons, one in an upspin and one in a downspin. And we use the term spin kind of colloquially. It tends to be more like if you think of a magnet with a north pole and a south pole, and one's pointing up and the other's pointing down. It gets called spin. It's a term that comes out of the standard model in quantum mechanics. But just know, at least at this point, that no 2 electrons can have exactly the same address. So in an orbital, you'll at most have 1 up electron and 1 down electron, and then that orbital is full. So that's why when I go back here and I draw in, let's say if we draw in the electron configuration of neon with 10, I could have on each one of these orbitals. So this is an orbital of a 1s sublevel, principal quantum number 1, sublevel S. There's 1 possible orbital in an S sublevel, so there's 1 line. Each line can hold up to 2 electrons, an up and a down. So this is principal quantum number 2, S sublevel, 1 orbital, 2 electrons there. And then the 2p sublevel, quantum number 2, sublevel P. Sublevel P has 3 possible orbitals, and I put my electrons in according to some other rules we'll get. But no line has more than 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, each represented by an arrow, and that would be an orbital diagram of neon, at least with lots of other messy little dots in it. Let's leave that. Let's go on. So if we do, let's say carbon. Carbon has 6 electrons, 6 protons, 6 electrons when neutral, so we'd be 1, 1, 2, 3, 4, 5, 6. So there's the electron configuration of carbon. And we could do something like uranium. Oh, I don't want to do uranium. Oh, that's a lot of arrows. I don't want to do uranium. Talk me into it sometime. Let's maybe do iron. What's iron? 26. Trying to do it off the top of my head. 26 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And notice, iron is in that middle group of the periodic table, that there's 10 elements across it. And so we end up putting our last electron in within this section of the periodic table that has 5 possible orbitals or 10 possible electrons fitting in there. So really, when you look at the periodic table, here are your elements that form the left side of the periodic table. Here are your elements that form the far right side of the periodic table. Here are the elements that form the middle part, and here are the elements that form those weird 2 rows that get pulled out at the bottom. Every element is placing its last electron within this particular block of the orbital configuration. So that first section of the periodic table is often referred to as the S block, because the last electron in something like hydrogen or sodium is an S electron. The far right side of the periodic table is often referred to as the P block, because the last electron going into the electron cloud is a P electron. The middle area is the D block, and then the lower 2 rows of the periodic table are the F block. And so this all links together, the periodic table, order of electrons, how it all goes together, and that then ultimately is all going to relate to reactivity somewhere down the road. So the orbital diagrams are what we've been working on, a representation of electron structure that shows electrons in order of increasing energy and represented by arrows. Typically, this can be done in either a vertical or horizontal format. We'll take a look at that in class. 3 rules to know about orbital diagrams. The off-bow principle, which Hund and Pauli here actually names a scientist, but off-bow is just a German word that means filling up or filling up in order. So this means that electrons fill from low energy to high. So they fill the lower quantum levels first, and then they work their way up. Hund's rule says that when you have more than one orbital, so like in our P's, you will occupy each orbital in a sublevel before you go back and fill it. So if you have a P sublevel, you'd fill it 1, 2, 3, 4, 5, 6. It is easier for an electron to create a new orbital at that particular sublevel than it is for it to buddy up with another electron. If you think about it, electrons are both negative. They're going to try and repel each other. They're going to try and stay as far apart as possible. So within the restrictions of the energy of that particular sublevel, the electrons will more happily create their own orbitals before they start to buddy up within the orbital. So that's Hund's rule. So off-bow, filling up. Hund's rule, occupy before you fill. And then Pauli exclusion principle, we've already said, is that no 2 electrons can have the same complete address, which basically simplified means 2 electrons per orbital max, because your only 2 possible last pieces of the address are spin state, up and down. So we're eventually going to tie this into an electron configuration, and I'll kind of leave it here that the electron configuration is a shorthand notation for locating all of the electrons in the atom using principal quantum numbers, sublevels, and a count of the number of electrons in the sublevel. And so, did I leave carbon up here? I don't think I left carbon. Let's do carbon again. 1, 2, 3, 4, 5, 6. So this is the orbital diagram for carbon. If we were to write this in a shorthand notation, it would be 1s has 2 electrons in it, 2s has 2 electrons in it, and 2p has 2 electrons in it. That would be the electron configuration for carbon. So we basically take these numbers, we list them off in order from lowest energy to highest, and then we put a little superscript telling how many electrons are in each of those sublevels. Chemists always like to have efficient ways to do things. The orbital diagram gives us the full orbital configuration. The electron configuration notation gives us more of a shorthand, and then that ties a lot into, again, the periodic table of the elements, and this idea of the octet is an ideal outermost electron configuration. There is a special thing about that magic number 8, but we have to learn in more detail what that is and when it applies and when it doesn't to then tie this into chemical reactivity. But for now, let's just work on figuring out where the electrons are